now. Is it good?
Good. The next speaker in our pre-lunch session is Wei Li from the Chinese Academy of Sciences, and in some ways she will start off where Nikita left off, starting with BPS crystals and going on to BPS algebras.
Okay, thank you very much for the introduction, and I would like to thank the organizers for this wonderful conference and for giving me the opportunity to speak here. So the title of my talk is From BPS Crystal to BPS Algebras. So this is based on the work that I did for the past 2-3 years. First with Masahito Yamazaki and then with Dmitry Galakov. So the main question we want to ask is that, give me a four-dimensional into-two theory. What is the algebraic structure that analyze the BPS sector? So this definition of the BPS algebra or algebra of the BPS states was given by Javier Moore in 1996 in their study of threshold correction of certain 4D into-two theory. So in this definition, the element of algebra are the BPS states, and the multiplication is given by the fusion of 2 BPS states into a third BPS state. So this is an analog of the chiral algebra of a two-dimensional into-two superconformal field theory. And is robust because it's about the BPS sector, and it controls many aspects of the theory, such as BPS counting or word crossing. So the system that I want to focus on today is the type 2A string on generic toric Calabi-Yau 3, and the half BPS sector is given by the de Bruijn wrapping holomorphic cycles. So the question I want to ask is, what is the BPS algebra of this system? So first, I will now derive this BPS algebra directly as a fusion of the BPS states, because that will be far too complicated for this system. And second, there are actually already different formulation of this BPS algebra. Some of them indirectly in different setups that are related by string dualities. So first, we have this cohomological Hall algebra, CoHa, which was defined by Kontaveit-Sweepermann in their study of word crossing. So this has been nicely reviewed by Yaping on Monday. And then this algebra also shows up in Costello and Gaiotto and many people in their study of the junctions in the omega deformed M theory. So for the C3 case, this is the alpha Yangian GL1. And moreover, we also have this truncated W algebra that show up in AGT or the Cornell VOA story. So because of this system are all related by string duality, which preserve the BPS sector. So if we consider the same toric Calabi-Yau, they should all these algebras should be essentially the same. So this is indeed the case for the C3. So for the C3 case, the alpha Yangian GL1 plays a central role. So if you start from here and consider the Borel subalgebra, so it has been shown by these people that the is isomorphic to the corresponding CoHa. And also the alpha Yangian GL1 is isomorphic to the universal enveloping algebra of the W1 plus infinity. So from there, you can truncate. You can first truncate to Wn, which show up directly in AGT, or you can truncate, have a 3-parameter truncation that show up in the Cornell VOA. So today, I'm going to use this alpha Yangian formulation of the BPS algebra. And we'll derive this alpha Yangian version of the BPS algebra based on how they act on the BPS states. So the advantage of this formulation compared to the other two is that it applies to all toric Calabi-Yau threefold in one go. Also, it's very easy to write down explicit relations. So for the type 2A string on generic toric Calabi-Yau 3, the BPS sector has an effective description of the include 4 quiver quantum mechanics, and the BPS states are given by certain 3-dimensional color crystals. So we can consider this as a representation of the BPS algebra, and we first fix how they should act on this representation. And from there, we can deduce the algebra itself. So because this is the generalization of the alpha Yangian of GL1, and the data depends on this quiver with potential, so we call this quiver Yangian. So this procedure applies to all Calabi-Yau threefold, and it's very explicit. And I will also show that it's very easy to generalize to trigonometric and elliptic version, and maybe even more. And also, this is also very easy to describe non-vacuum representations. So the set of crystals I want to use to bootstrap this algebra are the states in the non-commutative chamber. They correspond to the vacuum representation of the algebra. So we can also consider non-vacuum representation that cover other chambers, and we can also include open BPS states. So this is the plan of the talk. I just finished the introduction, and I was first review the construction of the BPS crystals, and then how to bootstrap the quiver Yangians, and also the trigonometric and the elliptic version. And then I explain how to describe the non-vacuum representation, and then end with a summary and discussion. So first, this type 2A string on generic Calabi-Yau 3 here. So I want to consider the half BPS states with the deep-brain on wrapping holomorphic cycles. So first, I will just consider just with one D6 and no D4. So this corresponds to the rank 1 Donaldson-Thomas theory. So the world volume theory that living on this deep-brain bound state is given by this equal to 4 quiver quantum mechanics. So the map from the toric data to the quiver data is one to many, and this map can be determined by the techniques this brain tiling techniques. So the quiver is consists of a bunch of nodes and a bunch of arrows between these nodes. So for each node, we have a UN gauge group, and each arrow we have a chiral field that transforms as a bifundamentals with respect to the two UN group at two ends. So for example, for the C3 case, we have one node here and 3 self arrow. And for the superpotential is the sum of the monomial of the chiral field. And each field appears exactly twice, once with plus sign and once with minus sign. So this is the superpotential for C3. So this property is precisely such that you can repackage this information of the quiver and superpotential into a periodic quiver, meaning that you draw this quiver on R2 periodically, and like this 3 arrows correspond to the 3 directions here. And in the fundamental domain, each phase corresponds to a term in the superpotential, and the orientation match with the sign. So for each deep-brain bound state, it corresponds to a T2 invariant solution of the F term and D term in the quiver quantum mechanics. And then it has a description of a 3-dimensional crystal that you can uplift from this periodic quiver. So the quiver data first get translated into the quiver with superpotential and then to the periodic quiver. And then this number of deep-brain bound states get translated into the rank of this quiver quantum mechanics, and then into the number of the atoms in this crystal. For example, for the C3 case, the set of crystal is precisely the set of the plane partitions. And the generating function of these plane partitions is just a Magma-Hom function, and which is precisely the BPS partition function in the C3 case. So for the C3, there's no compact D2. So the number of D0 just correspond to the number of boxes in the plane partition. And for the more generic case, the number of D2 and D0 map to this number of the colored crystals, and the generating function of the this color crystals reproduce the BPS partition function. So now let me use one example to explain how do you obtain this BPS algebra by uplifting this periodic quiver. So this is almost the simplest example other than C3. It has 3 colors. So it has 2 colors. So it's given by this Z2 orbifold along the first 2 directions of the C3. This is the toric diagram, and this is the quiver and superpotential, and this is the periodic quiver. So you see, because it is an orbifolding action, the color alternate along the first two directions, and they stay the same along the third direction. So before we start, there's one last piece of information that we need to fix. So we have this D6 spring that wrap the entire Calabi-Yau. So the gate degrees freedom is frozen. So we have this framing node here, and we have to draw. There's some arrows to the gauge node. So we're considering the non-community DT chamber first, which where the framing is that there's one arrow from the framing node to one of the gauge nodes. So this is the frame node. So let's set the number to be 1. And then in the periodic quiver, we just choose one node with this color as our origin. So in this uplifting, the path from the origin define atom. So for example, the origin 2 itself, this is the leading atom. And this path give you the red atom here. And this longer path give you the this blue atom. So because for each atom, there could be multiple paths that reach there. So we need a notion of the path equivalence, which is enforced by the F-term constraints. So for example, for this blue atom, these two paths are equivalent. Okay, so then you can just keep going. And at some point, you have a closed loop. And so you end up to the same node as before, but you're deeper in the crystal. So the depth of an atom is defined as the number of closed loop in the path. So for example, in these two figures, all the atom has depth 0. So there's no closed loops. So another way of saying this is that they're all on the surface of the crystal. So, and then I can close this loop, and then I add this atom. So this one and the one at the origin, they will both map to this node here. But this one has step 0, this has step 1. So in this process, there's this rule that used to be called a melting rule, but I'll just call adding rule here. So the rule says that to add an atom, all its precursor has to be already in the crystal. So a precursor of an atom is all the atom that has some arrow pointing to it. For example, the precursor of this red one is this blue one, and the precursor of this blue atom is this red one. So in this configuration, all the precursors are already present. So this is an allowed configuration. So for example, now if this blue atom has two precursors here, one here and one here, they're both pointing to this. So now in this configuration, only one of them is present. So I cannot add this blue one. So this is not allowed. You can also see that this is not allowed, not a valid plane partition. So, but if I add both these two atoms, now I'm allowed to add this last one. Sorry, both these red atoms, now I'm allowed to add this last blue one. So this set of crystals are the toric fixed point of the moduli space. So the crystal melting is an old story. So the new ingredient is that when we turn on the omega background, we want to assign the equivalent weights to each atoms. So each arrow has an equivalent weight, and the equivalent weight of the atom is just because this definition is just given by the sum of all the weights on its path. So this path equivalence means that we need to impose this loop constraint. The sum of all the weight along a path has to vanish. And when you project this a crystal state down to the periodic quiver, the atom that project to the same node should have the same weight. So if you want to specify an atom, you can give its weight and the depth. So this loop constraint corresponds to the global symmetry. So we can also impose a vertex constraint that corresponds to gauge symmetry. So if you impose both of them, then the number of parameters is precisely 2 that correspond to the 2 equivalent weight of the toric Calabi-Yau 3. So you can just do this for any quiver that correspond to the toric Calabi-Yau 3. So for example, this conical case, this is the periodic quiver. There's 2 colors. So the full 3D crystal has the shape of the pyramid with 1 atom on the top. So this is an example with a compact fourth cycle. So this Pico diagram has a closed loop. So it has the shape of the plane partition, and the color is given by this Z3 orbifold. So now I'll explain how to bootstrap this BPS algebra starting from these crystals. So the BPS algebra should act on the BPS superspace and reproduce the fusion process. So accordingly, we define the generator of the BPS algebra as changing the BPS state by a smallest unit. So the BPS state is given by the crystal, and the smallest unit is the atom. So for each color, we have a katon and the raising operator that adds the atom of that color, and the lowering operator that remove the atom. Then we first try to fix the action of these operators on any crystal, and from there we can find all relations of these operators. Then the BPS algebra is just given by the algebra that's freely generated by these operators and divided by all the relations. So because the BPS Cooper space is infinite dimensional, so we expect that this modes should also be infinite dimensional. So we organize them using this one parameter called spectral parameter. So this is the ansatz of this action of this unknown algebra on this set of crystals. So this is the katon. So the crystal is the eigenstate of all the katons, and the raising operator will add an atom of color A, and the lowering operator will remove an atom of color A, and the pole is given by the weight of that atom. And so now we just need to define this precise EF such that the EF are non-zero only when this final state are valid crystal states. So what I mean by valid? So in this previous example, if the initial state is this 2 atom state, then the final state of E action is given by this 3 possible 3 colored state, 3 atom state, and then this F final state is given by this 1 atom state. So how do we realize this? So then we refine this ansatz a bit more. So this precise eigenvalue function that we call charge function, we wanted to have this form. So it has a factor that's given by the vacuum, and then each atom in the crystal contribute a factor. So if we look at this charge function color A, so it's not just the atom of color A contribute, all the atom contribute, and with the relative factors here, and it's shifted by the weight of that color. And then the coefficient of the EF action is completely determined by this precise function also, by the residue. So this is inspired by the C3 case, by how this alpha Yangian GL1 acts on the set of plane partitions. So now we just want to, so now there are only 2 things that we haven't fixed, this ground state function and this relative binding factor. So the way we fix is that we demand that the poles of this precise K gives precisely the set of poles where you can add the atom and the poles where you can remove atom. So it should provide all the necessary poles, meaning that if you start from the vacuum and you keep adding, applying E operator, then you can generate the entire set of crystals. And where if you start from arbitrary crystal, if you keep applying F, you can reduce it to the vacuum. So the representation is cyclic. So also there's no redundant poles, meaning that the adding rule has to be satisfied automatically. So so because we're first considering the non-community chamber, the crystal start from 1 atom. So this is the form of the ground state. And so this is the binding factor we want to have. So for the contribution of the atom of color B to the precise A function, for each arrow from B to A, we have a one factor in the denominator. And for each arrow from A back to B, we have a numerator. So let me use this example to explain how this works. So this is the same example that I used earlier. This is the periodic quiver with the three weight here with this loop constraint. And we want to see how it generate automatically the crystals like this. So we have 6 building blocks. So 2 Guangxi charge function, 1 for each color, and 4 relative binding factor. So we just read off this from these 2 definitions here. So 1 to 1 and 2 to 2 are the same, and 1 to 2 and 2 to 1 are the same. So now we want to check that this is cyclic, meaning that we have all the necessary poles, and also the adding rules are automatically satisfied, meaning that there's no redundant poles. So let's start from the vacuum. So the vacuum charge function for the color 1 is this. So there's 1 pole at 0. So this 1 pole corresponds to the E1 action that can add this blue atom. And because there's only 1 pole, you don't have a pole for the F actions, meaning that you can, the F1 will annihilate the vacuum, meaning that you cannot remove anything from the vacuum. And for the color 2, there's no pole at all, so you can neither add a red atom nor remove anything. So this level, oops. Now this is the level 1. So the initial state is this 1 atom state. This is the charge function for color 1. It has 2 poles. So the pole at 0 corresponds to the pole that you can use the F action to remove this atom, and the pole at H3 corresponds to the E1 action where you can add this atom. And this is the charge function for 2. So these 2 poles correspond to these 2 positions that you can add this the red atom. So now let's check the adding rule. So this is the first place where this shows up, and it's also where the first place you see the cancellation due to the loop constraint. So it's enough to check this blue atom. So this is the initial state, and this is the charge function for color 1. It has 2 poles, and it corresponds to the 2 places that you can add this blue atom here. But then you see that we use up both poles. If I want to, oops. So we use up both poles. So now if I want to add this atom, then I can't. But this is good because this one confusion is not allowed according to our adding rule. The adding rule says that this one has 2 precursors and only one of them is here. So both the precursor has to be there. So you cannot have this configuration anyway. So if you want to add this blue box, you have to first add both of the red boxes first. So at the level of the charge function, this is realized by this factor that provided by this the last red atom. So it gives this pole where you can use to add this last blue atom. So you see, it's pretty automatic. So let's summarize. So the poles of the precise function encodes a position where you can add an atom or remove an atom there. So as you can see that when you add more and more atoms, the poles are always pushed to the surface of the crystal because of the cancellation that due to the loop constraint. And only the necessary poles are there, and there's no redundant poles. So the adding rule is automatically implemented. So now we fix the action, and we can just deduce the relation that's satisfied on any crystal. So the quadratic relation are very easy to fix. You just apply 2 operators on any crystal, and then you reverse order. And so then you immediately see this set of relations. And there are two easy ones that do not depend on the information of the quiver, and then these four slightly more complicated ones. So the information of the quiver shows up by this relative binding factor and some statistic factors. So then you can just read off the range of the mole expansion from the algebras action of the crystal. So this is the EF generator. From the action, you see that this is bounded from below, and the mole expansion for the precise depends on whether your toric Calabi-Yau has a compact first cycle or not. So for the case without the compact first cycle, the quivers are non-chiral, and this binding factor are homogeneous. So the precise, the mole expansion of precise bounded from below. For the case with the compact first cycle, the quivers are chiral. So this is inhomogeneous and it's not bounded from below. Then you just plug in this mole expansion to these relations, and you take singular terms, and then you deduce the relation in terms of the moles. So the first two are easy, and this can be more complicated. So this is precise E relation for the C3 case. And this has been checked experimentally directly from the input force quiver quantum mechanics by Dima and Masahito. So so the quadratic relation are easy. So we can similarly try to derive the higher order relations as kind of experimentally. So, but how do we know that when we find all the higher order relations? So because the BPS algebra should capture the entire BPS superspace, the vacuum character of the BPS algebra should reproduce the BPS partition function, which is reproduced by the generating function of the crystals. So demanding this will determine all the higher order relations. So we have reproduced the set relation for the upper-endian gel n/m. So this is the C3 example, the upper-endian gel 1. And yeah, so we haven't got around fixing the higher order relations for general quiver Yangian. So this is still an open problem. So this is an example for this set of toric Calabi-Yau. The quiver Yangian reproduce the upper Yangian gel at m/n. So this formulation is also very easy to generalize to trigonometric and elliptic case. So in this binding factor, so earlier we just have these rational factors. So now if you replace these rational factors by some sinh function or the theta function, you reproduce the trigonometric and elliptic, you generalize it to the trigonometric or elliptic version. So one complication is that for this trigonometric case and elliptic case, there can be central extensions. So for generic central term, the crystal actually know the representations. So what we did is we first bootstrapped algebra from the crystals without the central term, and then we turn on the central term and fix the remaining bit by the consistency, by associativity. So and then we also confirm this from the gauge theory. It's a 2,2,2 theory on S1 for the trigonometric case, or the 3D n=2 theory on torus for the elliptic case. So let me now explain how to study the non-vacuum representations. So far, the crystal we use always start from one single atom and grow infinitely. So this is realized by the form of the Guang-Sei chart function. So this O is the number of the frame node, and it is always like this. So for example, the shape of full crystal is this infinite cube. It's supposed to be infinite, and this is this pyramid with one atom at the top. So translate into the framing, that means that there's always just one arrow going from the framing node to the frame node. And this will correspond to counting of the closed BPS environment in the non-community DT chamber. So can we describe also, can we include open BPS states or go to other chambers? So by open BPS states, I mean that I add D2 wrapping a holomorphic disk that ends on a D4 and that wraps on a non-compact Lagrangian cycles in the Calabi-Yau 3. So for example, for the C3 case, the closed BPS states is given by this ordinary plane partitions. For the open case, the plane partition has this non-trivial asymptotics. So the asymptotics are labeled by 3 Young diagrams. So, and you can also go to other chambers by changing the stability condition. For example, for the resolved conical case, the shape of the pyramid for the non-community chamber has just 1 atom on the top. So for other chamber, you have more than 1 atom on the top. So this has 3 here. So how do we describe, first, how do we describe crystal with a different shape using the canonical crystal? Because we know how to describe the canonical crystal. So the answer is that for a given quiver with superpotential, we can think of this crystal with other shape as a subcrystal of the canonical crystal, because we're now changing the internal structure. We're just changing the boundary where you can grow your crystal. So, and then we can decompose arbitrary subcrystal as a superposition of the positive and negative canonical crystals. So let me show you quickly how this works. So I just draw this in 2D. So this is the shape of the canonical crystal. Suppose I want to describe a crystal that has this shape. So first we look at the starting point of the subcrystal, and then we determine the position of the 2 positive crystals. See, they can be think of the superposition of these 2 positive crystals. And then when you go deeper, they start to overlap. So to avoid double counting, you want to add a negative crystal to cancel this. So if you have many negative crystals, then when you go deeper, this negative crystal will also start to overlap. Then you have to add some positive crystal to cancel the overlaps of the negative crystal. So, and then you just keep going until you reproduce the shape that you started with. And finally, you can also truncate the shape of the crystal by adding some negative crystal by hand. So this is useful when sometimes you want to describe a 3D slice of crystal. For example, in the C3, the plane partition gives the McMahon module, but sometimes you want to consider the Fock module that's spanned by Young diagrams. So in this way, you can generate pretty general, simply connected subcrystals. For example, in this case, we have 3 atoms at the top. You can realize by having 3 positive crystals that start at the 3 blue dot, and then the 2 negative canonical crystals. So this subcrystal will describe non-vacuum representations. So this representation is in the information is entirely in the ground state chart function. This is for the vacuum. This is for the non-vacuum representation. So for the non-vacuum case, each positive crystal, if you look at the first atom, it provides a pole, and each negative crystal provides a 0. So the reason why this is a vacuum and this is non-vacuum, because this one grows the slowest. And because you're changing the ground state function, that will also change your mode expansion. So accordingly, you need to define, you need to change the mode expansion of the precise. So that's defined as the shifted quiver Yangian. So now we have a family of quiver Yangian with different shifts here. So to translate into the framing, for each positive crystal, you have arrow going from the framing node to the frame node, and then for each negative crystal, you have arrow back, and then you need to add some superpotential terms for the new arrows. So let me summarize. So I've explained a method to construct the BPS algebra for the type 2A string on generic toric Calabi-Yau 3. So we use this description of the BPS state in terms of the 3D color crystal, and we first fix action of the BPS algebra on this set of crystal, and then from there we can deduce the algebra relations. So this is how the quadratic relation looks like. So I've also shown that it's very easy to generalize to the trigonometric case and elliptic case. And also the subcrystal or different framing describe non-vacuum representations. So then some applications. So this subcrystal representation include different chambers or an open BPS states and even more. So for all of them, the generating function of the subcrystals, set of subcrystal would reproduce the BPS counting. So there's a efficient way of computing this generating function. You just count the poles of this chart function at each level. So there's a mathematical code written by Boris, which you can find in his website for some examples. Also, we have used this to derive the beta-ansatz equation in the gauge beta correspondence. So instead of spin chain, we now have a crystal chain. So for each side, we have a crystal representation. And we can write the Lux operators and transform matrices and off-shell beta vector all in terms of the BPS algebras generators. And the beta-ansatz equation reproduce the vacuum equation of the corresponding quiver gauge theory. And some possible future direction. First, it would be nice to translate to other formulation of the BPS algebra. For example, for the CC case, the alpha Yangian one is isomorphic to the universal developing algebra W1 plus infinity. And for all the cases without the first cycle, I suspect that it will be alpha Yangian G maps to the G extended W1 plus infinity, where G is either GL M/N or this D21 alpha. Also, it'd be nice to map to this doubled cohort that Yaping discussed on Monday. Also, there's another way of constructing this set of algebras by this gluing construction. So here we just use the toric data directly. So for each vertex in the toric diagram, we have a C3. So we have a alpha Yangian GL1 for each vertex. And then for each internal leg, we just add a bunch of additional operators that transform as bimodules with respect to the two corners. So the representation will be, so for each vertex, there will be a plane partition, and then the whole thing will be some glued plane partition. So we first fix action on this glued plane partition, and then we fix algebra. So this has been done for these two simple cases. It might be useful. It might be interesting to see how far you can push this. And then for the same toric Calabi-Yau, you can map to, sometimes you can map to different quivers, and the quivers are related by the quiver mutation. So we conjecture that the quiver Yangians is related by quiver mutation are isomorphic. So this is true for the alpha Yangian GL M/N, the super case, and it would be nice to check whether this is true also in general. And also, I've seen that we can study pretty general subcrystal representations, and many of them don't have a interpretation of the deburring yet. So it would be nice to fix this and then see what kind of BPS counting problem they correspond to. Also, can we generalize to Calabi-Yau fourfold or more? Okay. Yeah, thank you for your attention.
Thank you, Wei, for ending well in time. First question from Nikita.
These generators E, F, and H, which you constructed algebraically, or you have some physical interpretation of what they do?
Say again?
The generators of the Yangian, where do they come from?
Should I give the talk again? So this is the one slide that maybe I went too fast. Yeah. So the algebra is originally defined as given by this fusion. So now the algebra should also act on the BPS Hilbert space. So we want to define in such a way that you can reproduce this fusion process. So in particular, we want this BPS algebra to map any BPS state to another BPS state. So we define this, so that's why we want this generator to change the BPS states only by a smallest unit. So this will guarantee that that you can also this cyclic condition that will guarantee that you can use this to map any BPS state to another BPS state. So so this is just a free generator, and then you model out by all the relations.
So
and then,
what BPS states do these free generators correspond to?
I mean, they don't correspond to a particular BPS state, but they reproduce the fusion process. Or you can think of, you can ask if I have a BPS. You
start with Harvey and Moore, so you're supposed to have two states which scatter and produce the third one.
So if you want to realize that, you can take a arbitrary K, arbitrary crystal, and for that I can write this as a bunch of racing operator that's acts on the vacuum and with some contour integrals. And then you take these two K1 and K2, and then you just see how the operators they change. How they flip. But that's, I mean, yeah, that's yeah. I mean, if you really want that information, you can get it, but it's not very.
So what's the physical process which leads to this? So what do you do in quantum mechanics, or where are you doing this?
Where I do what? So in the quantum mechanics, you're changing this adding. So in the quantum mechanics, you're changing the rank of the quantum mechanics.
How will you not do it? You do it interface, or what do you do?
Yes, you have interface that you change the rank at the level of the quantum mechanics. You change the rank of the quantum mechanics. Yes.
It's a question up there.
Yeah, thanks for the beautiful talk. So as you explained, these modern crystals are relevant for counting these frame BPS states in the non-commutative chamber. On the other hand, the relation, so you have the same kind of similar crystals which appear in the tropical vertex when you want to count states close to large volume and make relation to the topological string amplitude. So the question is whether you can identify the subcrystal corresponding to large volume chamber in some way.
I mean, that would be like infinitely, if you start from the non-commutative chamber, if you want to go to the topological chamber, that would be infinite steps of work crossing, right? So it's not very feasible to do that. Yeah, so this
you
is
have to take some kind of inductive limit.
Say again?
You have to take some kind of inductive limit. Take some subcrystal which is larger and larger, and take a scaling limit so as to extract the logical sum.
Yeah, but I don't know I don't know how realistically efficient that is.
Okay, thanks.
Okay. Any other questions? So before we thank Wei, I just want to remind people there'll be an announcement right now, and afterwards the group photo. So let's thank Wei once again and all the morning speakers.